crack relativity step 3. We cover the last part of special relativity and the basic part of the general relativity here. Okay, so there is another way to present the special relativity is called Minkowskis World. In this world, he take the coordinate u equals c t1 and x1, and according to assumption, nothing can go beyond speed c, and second assumption is every frame see the same speed maximum. Okay, so with this requirement, he tried to come up with the relativity equation. Now Lorentz initially cleverly come up with the basic special relativity coordinate conversion, and that was a try and error, and very clever to come up with one working. Now Minkowski is going to use this requirement and lead this basic equation. He mathematically proved that the only things you need is the requirement, then come up with the relativity equation. You remember relativity equation? Okay, so what he did is he defined the world in the coordinate like that, and this is called our world because everything will be in this. You can never exceed light speed. Okay, so if it's one dimension, two dimension, it's going to be a cone, like so this is going to be our world. Okay, you see many literature talking about this. So he needed to use some scaling factor, and these requirement about the speed, inertial frame speed. Okay, then this is going to be a few pages of derivations. It's going to be too long, so we need to skip. You have to look at the textbook, but he came up with actually the equation here. Beta is the b over c. Okay, so this basic relativity equation is purely coming from the requirement of there is a maximum speed and every frame sees the same maximum speed and scaling factor. That's all he needed to derive this equation. So he kind of cleaned up the theory of relativity, where it's come from. The Einstein started with Lorentz coordinate conversion. It's cleverly made equation, but with this theory, it became like this is the only conversion equation that satisfy those requirements. Okay. So Minkowski's world is significant in that meaning, and also it's kind of give you the basic invariant. The concept is invariant. That means every frame should have the exactly same physics law within. Okay, so that's also guaranteed by this consideration. Okay, now we go to the general theory of relativity. What it's about is in order to deal with non-inertial frame, you have to deal with force acting, and we have a force acting like that. This is Newton's law, and also another force is gravity force. Okay, and mass is used on both sides, and Newton puzzled, are they really same thing? And he couldn't come up with any. He didn't formally said they are same. It's just left it vague. And Einstein said this is a principle, that this mass is same as this mass. Okay, so why he needed that, I tell you later. Okay, once he assumed this, then let's talk about it now. Okay, what happened is every acceleration is coming from gravity. So what do you mean? If you give a force, you push something, it's not from gravity. Okay, the Einstein ignored these cases. He handled only the force generated by gravity. Okay, so he said every force generated by gravity, the gravity is also generated by the curve in space. Means the space-time is curved, and if you are here, you get the gravity, the force. So you need the counter force to stay around. Like this is the sun and the planet going around. Okay, so this the circular motion produce the acceleration. This acceleration counter with gravity, so it work out well. Okay, so for Einstein, the mass that produce the force, the mass that produce gravity, they are equivalent by general theory of relativity, which is both come from the curve of the space. Both come from that's why they are same mass, and this curve acting on mass, and sometimes it's acceleration and sometimes it's gravity. So everything is unified into this. Okay, so the gravity causes a time dilation. In this Einstein equation, time is also individual to the frame A and the frame B, and this time it's not just inertia. Frame A is getting some force, gravity or any kind of force, then time tick a different speed, and this has a different force. This also time tick a different speed. So time dilation is calculated, and this is the equation for the gravity causing time dilation, and this is often used like a black hole. And also, since space-time is curved, say you have a sun here, and the famous experiment is in the eclipse, you shut off the sun's light, then you could observe the star behind the sun. Okay, so the light bend, and when light bend, it's act like a lens. So actually it's look like a star, look as if it's here, it's moved because the light bend. Okay, so that's a famous experiment. So this was confirmed by observing the star behind the sun during eclipse. Okay, now also there is a argument about, is cosmos straight or it's curved, as Einstein said, which way it's curved, and many discussion has been made. Maybe cosmos is bent, concaved, so if you go this way, eventually come back here, or cosmos is flat, or cosmos is bent like that, like a saddle shape. Okay, so that's affect the parameter in the universe, and those discussions started using Einstein's theory, and the Mercury is going around the sun, but it's gradually changing this ellipsis orientation. It's called the precession, and precession of Mercury is never been explained by Newton's law, but general theory of relativity successfully explained this. Okay, so black hole is a very important discovery when the huge mass exists. So because mass bend the lights, and some lights come close to black hole, it's just sucked in, and even light from black hole itself is bent and sucked in, so you cannot see anything but just black. That's a black hole. And when light come very close to the black hole, there is a area that the lights bend but escape or sucked in. This boundary area is called event horizon. Okay, and that's define the size of the black hole. And now Einstein's general theory of relativity apply only for the gravity. Now there are four known basic forces in this world. Is electrical force, okay, and strong force inside the nucleus, and weak force inside the nucleus. And beside the gravity, there are four basic forces existing, and Einstein equation made for the gravity. And electric force, now we know magnetic force is just another form of electric force. Einstein tried to combine electric force into this theory and wasn't successful. He called that unified theory. Okay, the force inside nucleus is still far away. At least he tried to combine electric force, but wasn't successful. It's called unified theory, and it's still the subject of physicists, how we combine everything together into the single theory. Right now, the Einstein theory and Maxwell's equation still independent. So Einstein and Maxwell and nuclear physics has a strong force and weak force. So those are the type of force. And we know the Maxwell's act on mass just like the gravity, but the theory is independent from the Einstein's. Okay, so The basic part of the general theory of relativity is that's it. Is there is a basic equation for that, but that's include the differential geometry, the tensor calculus, which the it's not a subject here. It's beyond our video here, so we don't get into that complex equations. Okay, I hope you enjoy this video, and please check out the video too and subscribe.